Today's Bob Pease Show is brought to you by the properties of the Hearst Electronics Group, including Electronic Products Magazine, IC Master, and EEM, the #1 directory for electrical engineers looking for components and suppliers. The Hearst Electronics Group, delivering new and exciting products serving electrical engineers, including a new reference directory, daily product highlights on electronicproducts.com, and newly planned upgrades to IC Master. The best place for you to start is electronicproducts.com.
Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
Good morning. Good afternoon. I don't know where you guys are. I don't know when this is going to be played, but this is the Bob Pease channel. And in this channel, it's Bob Pease all the time. It's always Bob Pease. I'm sorry as hell, but that's what you get with Bob Pease, staff scientist at National Semiconductor, and Nick Gray, senior applications engineer. Hi, Nick. Good morning.
Good morning, Bob. Good morning, everyone.
And good morning, Paul Grohe, product applications engineer.
Good morning.
Oh, my goodness. And we're off on fun. Now, Nick is an expert on ADD converters, so if you have a question on driving an ADD converter, you ask me, and then I'll transfer the question to Nick.
Hey, wait a minute, Bob.
Yeah.
You know, while driving ADDs may be a problem, but you know, it's not the only...
It's a good problem.
Yeah, it's a good problem. And there are issues. But you know, it's not the only problem we have when we're dealing with these guys.
You mean like layout?
Oh, layout is very important.
Well,
and that's actually, layout is the biggest problem people have with these things. But you know, this is another subject.
We'll discuss it later. Yeah, but that's a good point. And Paul Grohe is a measurement expert, and he can measure almost everything I can except, you know, that LMV2011, which by mistake we're going to be discussing today. We got to look over the gain on that because you and I and your machine and my machine don't agree. We'll discuss that later. Not a problem.
Okay.
Very good. What topics are we going to cover in this series? We're going to cover all kinds of analog stuff. Topics that don't fit into a column. You guys all know my column in Electronic Design Magazine. Well, that has analog stuff. It has also crazy stuff, like recipes. We're not likely to have a recipe on. We might have a recipe, but not very often. But we're going to have analog stuff all the time on this video presentation. And we also invite your suggestions on analog topics. What do you think we should be talking about? Now, this video presentation is also sponsored by the letter A, such as analog stuff, amplifiers, ADD converters. Nick is the analog ADD converter guy. Analog University, answers for questions, and audio. The letter A is our primary, well, it's our secondary sponsor today. Analog University, did you know that NSC's Analog University provides low cost, no cost education, teaching and training on many linear and analog subjects? Did you know that Bob Pease is the dean of NSC's Analog University? Well, you can look it up. If you go to www.national.com/analogu, that's not very legible, but we'll fix that, to learn more about our programs. And we would also like to thank our sponsor. Let's shovel all this into one envelope and bring out the next envelope. Don't worry about that. Which is, Q&A. We invite questions on analog topics. Send me questions to Bob Pease, mailstop D25978. My mail address has been thrown away 34 million times. My mugshot has been thrown away 34 million times, but maybe 4 million people have saved it. We don't know. Or send to rap@galaxy.nsc.com. And we will answer questions as soon as we can. We'll answer some of the questions on the air in a month or two. We can't answer them next month because the timing is not right, but as soon as you ask us questions, we'll try to get you an answer. For example, a guy asked just the other day, how can I make a synthetic floating inductor? I looked up in our linear apps book, said, what's a floating inductor? And it said, here is the floating inductor. I said, I knew that, but this one while it looks like an inductor, this looks like an inductor with parallel with a megohm and series with 1 ohm, which would be a very good inductor. This would be a 1 Henry inductor. But this is a grounded inductor. He wanted a floating inductor. How do you do it? I looked at this and 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 I said, why not? Take 2 of them. You can't do it with less than 2 op amps. This looks like L, this looks like L. This makes a floating inductor. I haven't built it, but I'm going to build it one of these days because it's such a good circuit. I have a circuit with several 2 Henry inductors in it. It's a monster. I'm going to compare them. Well, it's still running. But what if the offset is a millivolt? If you have a millivolt error here, you'd have a milliampere of current. That's kind of messy. How is that going to work? And we'll explain that later. Hey, Paul, hold on to these 2 things because we're going to discuss those guys later.
Okay.
And we'll put this garbage into part 2, and we'll throw it on the floor. And we're going to throw part 1 on the floor. Now, I want to talk about some new, neat analog products. I guess National Semiconductors is partly a sponsor for this, and we're going to talk a little bit about the LMV2011. Isn't that amazing? We just had an application for the LMV2011. We have features. Low offset, 35 microvolts max, but 1 or 2 microvolts typical. Low noise, no 1/f noise, 35 nanovolts per root hertz. Very high CMRR, PSRR, gain, good bandwidth, good slew rate, blah, blah, blah. Good features. Applications, oh my gosh. Floating. Inductor. So we can take a couple of these LMV 2011s and put them into here. Now, what if the offset is 5 microvolts or 35 microvolts max? That means you'll have 35 microamperes max in here. That's a pretty good inductor. This current will not be the same as this current, but if it's small enough, nobody cares. Hey, Nick, do you want to bring out your A/D converter stuff now?
Yeah,
Let me just back out of the way.
Yeah, we were talking, I can just sit there. We were talking about the driving A/D converters. You know, I find the LM86702 is really a great amplifier for driving A/Ds. When you look at this, you see that the noise performance is quite respectable. As a matter of fact, it's very good. And you look at the voltage noise, and we're talking about 20 nanovolts per root hertz. And your inverting current, the worst case, you know, at any frequency of interest for most products, we're talking about what? You're talking about 200 picoamps per root hertz. That's very respectable, very respectable. When you look at the noise, we have over here plots of second and third harmonic performance. You see that this is fantastically good at 8 bits and even at 10 to 12 bits at 30 to 50 megahertz. It's still very respectable to 10 bits and even to 12. I mean, this is a really, really nice amplifier. Okay,
I'm impressed.
So I like this guy for driving A/Ds. It does quite well, especially your high-speed products.
Good.
And then we have a relatively new family of A/Ds. We're calling these the ADCS 7476 family. But when you look at the performance of these guys, it's really remarkable. An INL of 0.4, DNL 0.5 for the 12-bit product, and boy, when you get down to 8 bits, look at that. INL 0.05, DNL 0.07. I mean, there is no distortion here. And that gives us an effective number of bits for the 8-bit product of 7.96. You round that to the nearest 0.1, and you have an ENOB of 8. An effective number of bits of 8 for an 8-bit product?
I'm impressed.
I mean, this is a theoretically perfect device.
Nick, next time you run that damn thing, I got to go over and look at it because I want to see how it runs.
Great.
Okay,
hey, we'll have you take a look at that thing with our Wave Vision system.
Yeah.
Our Wave Vision system is our evaluation product. Well, let's not get into that now. That's a whole other subject.
That's a whole big subject.
I can get onto that and never get off. It's so much fun to work with.
How many hours do we have today on this tape?
Yeah, okay.
Half an hour.
Let's cut this one off right now.
We'll
very nice
off.
product.
You scoop those up, but we'll be back and look at those later. Oh, this is the main good stuff. Show that in too. Not a problem. Today's main topic is analog computers and analog simulation. as opposed to digital simulation, which means things like SPICE, which we will not throw heavy rocks at today. We'll let you draw your own conclusions about how much SPICE lies to you. But SPICE lies to us. It tries to lie to us every week and every month and every day, but we won't let it. Now, I had a column back here. I forget which month. Analog computing stuff. Anyhow, part 2 with a circuit. And let's see what we got here. We got a signal input, and when the input bounces up in the air, the output should bounce around and follow it up, etc., up and down. But it's going to be late. It's going to be bouncy.
What is this circuit modeling?
It's modeling. It's modeling a car or actually one wheel of a car. Thank you for pointing that out. Well, we got an inverter, and the inverter is trivial. It just says we had the wrong sign at the input. When this goes up, we want this to go up. This goes up, this goes down, this goes up. What's this stuff? This is a mass and a spring. What's the mass? The mass of the car. Are we going to talk about the mass of the wheel? Later. But if you have a car that goes bouncy up, the mass of the car would bounce and bounce and bounce. Now, Nick, have you ever ridden in cars that didn't have shock absorbers? Like a Model A?
I have never ridden a car with no shock absorbers, but I have ridden in a car with very poor shock absorbers.
And did it bounce like heck?
Oh, it sure did. It may as well not have had the shock absorbers.
But why are shock absorbers there? Not to make best comfort for the riders, but to make sure the wheel stays on the ground. Because your wheel is bouncing like heck, and it's not on the ground. You turn the wheel and nothing happens because the wheel is not on the ground. It's important to keep the wheel on the ground. The shock absorber, this is a shock absorber, keeps the wheel on the ground. Ooh. Now, mass, integrator, inverter, integrator. We have a wheel we have a car that's bouncing off the ground. But we have a shock absorber that says, damp it down, damp it down, damp it down. But it might have different damping factors for up and for down, because really, shock absorbers are different for rising and falling. So we have nonlinear up and down coefficients, which we'll see in a minute over at the bench. And we have a differentiator to make sure that we're fair. We have all this stuff. We have integrators. I think I also have a whole bunch of equations. Anybody needs the equations. The mechanical forces on the car's mass are thus and so. F equals m dv dt. Now, why a nonlinear damping factor? Because I already said that. Because the shock absorbers are different going up and going down. Why different damping factors? Blah, blah. What changes did I make in this circuit? Well, when we get to see it, the rep rate is a little blurry, rattly, wobbly, but it'd be much worse if I kept all these capacitors. 0.1, 0.1, 0.1. I cut them all to 0.01 because it would have made a lousy display. Now, as an analog computer, it's perfectly valid, but it's much better to see what's going on if you cut the capacitors. We are not going to have stupid pet tricks. We're going to have stupid digital tricks. Now, my old hiking friend, Ron, asked me, hey, Bob, is this for real? Well, is what for real? Is this for real? Well, it might have come off a website, but it's a case study of a car on a washboard road. And it defines a function which gives the car's function rattling up and down as a function of the speeds and the bump wavelength. And I looked at this and it said, oh, this looks like my analog computer, except it said bumpy road with 2 meters wavelength. You guys who know how to drive on washboard roads know it's never a 2 meter wavelength. That'd be a disaster. 2 feet, 2 feet minus 3 inches, 2 feet plus 3 inches, around 2 feet. Cars, trucks, fast cars, slow cars. It's always 2 feet wavelength. And it said that if your shock absorbers are shot, this is going to jump around and it's going to have a very bad resonance. But if you can go faster, it's not so bad. And if your shocks are good, you can drive up there without much problem. And I looked at this. I said, something is not right. Something is bogus. The ratio of amplitude of response to a bumpy road with a 2 meter wavelength, and I went on to the next page and they got a 20 meter wavelength. Now, if you try to get on a 20 meter wavelength on a road, you're going to go ka-womp, a whomp, a whomp. At 100 miles an hour, it's going to go ka-womp, a whomp. You can't do it. So this is a conceptual, a theoretical problem, but you can't do it. And even at 2 meters, I don't want to drive on washboard roads with 2 meters wavelength. But it was something fishy. What if you're going 40 miles an hour and the wheel is bouncing up and down, 4 inches or something, and there's same amplitude of input as output? It means your head is bouncing up and down at 4 inches amplitude at 40 miles an hour at some horrible number of cycles per second, which works out to 54 Gs. You want your head to come off, get in the car, follow this equation, go 40 miles an hour, and your head will fall off at 54 Gs. No, this guy doesn't understand. The amplitude decreases. When you're going 40 miles an hour, it's not that bad. Whereas he says the amplitude goes to nothing at 0 miles an hour. Well, so I sent him an email and he said, Bob, you don't understand the thing. So let's see, is there anything else in here? We've covered the bogosity factor. Where's the bogosity? Yeah, beware of bogosity. You guys know Tomer Moyatsi. They talk about the bogus factor or the bogosity factor, and there's a lot of bogus in there, so we're going to ignore that one. Now, do we have stupid analog tricks? No, we have wise analog tricks. What are we going to do? First of all, we're going to take this old circuit. What did it come out? 33103. You can go to the website. If you go to my website, a piece of paper, man? There we go. This will do. I forgot to list my website. www.national.com/rap. And you go there and you click on ED columns. And you click on analog computers. And then it leads you to this column. Okay, paper. And what I did was I added to this circuit a slightly improved model of wheel. Why is it improved? Because the model was that the old wheel would bounce up and down, and every time it goes over a bump, it follows the bump. But wheels don't do that. They bounce up on the top of a bump. They float when the ground goes way underneath, and then they hit it harder. Well, guess what? This circuit does that. This is a peak reader from a rectifier circuit. So we put in this right scale factor, approximately correct scale factor. We got a diode and a resistor and a wheel bumping on the ground. This is the inertia.
Ah, Bob. But
please.
Capacitor, unless it's pretty leaky, you know, it's going to hold that peak charge. It's going to stay there.
Well, this is going to ground, a virtual ground, and we also have a pull down to minus. You are correct. You are correct. Thank you. So let's mosey over to the bench to see how this thing runs. And we'll come back and do some other stuff. Okay? I'm going to get a dot of water and bring it with me, since that's the easiest way. This is an analog computer. It's got 2 dual op amps. It's got capacitors. Now, the smaller capacitors, the larger capacitors, the yellow ones were 0.1 microfarad. We put in the orange ones, which are 0.01. We are putting in a sort of a square wave from this little HP function generator. And we put in a positive step. The road goes up and the car goes up. And it bounces a little bit, but not too bad, unless we change the coefficient. Whoops, look at that. The shocks are getting worse and worse. Can't see it. Yeah. And how about if we change the other shock, the other factor of the shock? Oh, it starts ringing, and pretty soon you got no damping, and the wheel is bouncing all over the place, and the car is bouncing all over the place, and even the input square wave, the road is being deflected because we got so much noise. And with a shock like that, you wouldn't drive very far at those speeds. You wouldn't get very far. In fact, the output is twice as big as the input, which is pretty awful. So we're not going to be using that kind of shock. Now this is a step response, and you hit a bump with your car, and a step response is a pretty good representation of what's going on. But what if you're on a washboard road? Aha! We reach over here and change the thing from square wave. Let me put a triangle wave first. See, triangle wave is not so bad. You get bumpy bumpies, but it's not as bad as square wave. But we'll put in a sine wave. Now, you're going on a very slow bump. You're going very slow, and you go up and down, up and down. You're getting seasick, but at least it's not ripping your head off. And you go faster and faster. I'm going to reach up here. I'm going to pull this another inch closer, and you go faster and faster. And my goodness, the damping is lousy. But as you go fast, pretty soon the amplitude goes down. And you go faster and faster, and the amplitude is way down. I'm not going to fool around with the frequency, time base. So you go even faster, and it's even smaller. So you go real slow, yeah, you start getting significant bumps. So when you slow down on a washboard road, you got to watch out for these problems. You go fast. Now, in this case, we were driving the signal directly into the analog computer. Now we're going to drive it into the... What's going on? Why is that looking so lousy?
Backwards.
Did I do that one? Ah, good point. Thank you. You were right. Let's put this signal. Ah, the wheel is bumping over the top of the washboard.
Oh, wait a minute, Bob. What did you change here?
I'm driving through the wheel. Before I was driving the axle directly, and the bumping was forcing the axle. But now we're driving the road, and the wheel is bumping over the bumpy road.
So you've accounted for the rubber in the tire.
Yeah, we're using effectively the rubber tire. Now, this is not a good model. This is not a really true model because the shock absorber over here would ideally affect the bumping. It keeps the tire from bumping. Well, this shock absorber has no effect on the tire. So this is not a great model, but it's a pretty good model of a tire that's bouncing off the road and it's bouncing over things. So as you go faster and faster and faster, the tire is bumping off just the top of things. Ah, that's a bad picture, but that's okay. So the faster you go, the more the tire floats over the top and the less the car bounces over the top. Whereas the maximum, 100 hertz, when I built this thing originally, it was around 10 hertz. That's the right ballpark. So this resistor diode capacitor represents the pretty good rubber wheel and tire representation. We got three dual op amps, which covers everything. We had LMC6482s in there. I like to use duals. I hate to use quad op amps. I have to add extra wiring for the power supply, but I'd much rather use duals than quads.
Why is that, Bob?
Well, first of all, quads don't take any less space than duals. Than two duals. They save you a little in money, but they're lousy for versatility, and it's hard to get all the connections made to them. The connections have to be further away, whereas with duals, the connections can be closer. That's my opinion. As you can see, I'm using high-quality copper-clad ground plane with alternate connectors that work pretty well. Solderless. Okay, so that's our demonstration for this afternoon. We'll have more next month. Let's go back to the table, guys. What else do I have? Ah! Oh yeah, we have this stuff to finish. We haven't finished this stuff. For instance, a guy asked me the other day, how about an analog computer problem designing a lunar lander using a couple of integrators? Well, one integrator represents velocity, which is the integral of the force times compared to the mass, and the other one represents the position as a function. Well, that's the same integrator we're talking about here. It wouldn't be a closed loop, it'd be open loop, and you have to servo the force, the throttle control, and you need another integrator to tell you if you're running low on fuel. So the integrator of the force tells you not only the velocity, but you have to integrate the velocity without the gravity to, tell you if you're running out of fuel. And your speed goes up, and your velocity, your x position goes down, but you have to slow it down just right, which is not that easy, as anybody who has played those old video games knows. But you don't need a video game, you need 2 or 3 op amps. By the way, do you know anybody who'd like to design a 5-digit DVM using only vacuum tubes and parts from 1940? I've been thinking about that. I've thought about being locked into Polypac's place overnight and being asked to build a 6-digit digital voltmeter by morning, but that'd be hard. And designing a 6-digit DVM using 1943 parts is hard. Now, one of my friends had a question the other day. What if analog people can do stupid things? Can stupid people do analog things? Yeah, stupid people can try to do analog things. They just use SPICE. And SPICE gets you in trouble. Now, I'll get your guys' opinion on this, but my basic comment is SPICE can probably design simple and trivial and not high-performance analog circuits. Can SPICE or CAD design provide high-performance analog circuits? I don't think so. Why don't we just use CAD and let it design analog circuits and systems? You think it's a good idea? You think you can design analog circuits with CAD or SPICE? I don't think so. What do you think? Frequency? Settling? Fast settling? Low noise? High accuracy? Low distortion? Good layout? Oh man, how is SPICE going to help you with good layout? How do you know what good layout is? Most people who do good layout know what good layout is. How about crosstalk? How about strays between adjacent stuff? Oh man, this is a mess. Nick, your comments. You're first.
Well, I really think SPICE has its place, but I think you kind of hit the nail on the head.
Where's the garbage can? Where's the trash can? You guys got to provide a trash can next lecture, but anyhow, go ahead. Sorry, Nick.
I think you hit the nail on the head, Bob, when you said that SPICE is good for some things, or you indicated it was, but you said that it's not going to give you high performance results, and that's true. You're not going to get the performance that you really want with analog circuits when you're using SPICE, but for a first cut and for an indication of what's going on, are you on the right track, SPICE can give you an indication there. Yeah, you don't believe it. All right. Nah. We'll agree to disagree.
Yeah, your comment.
Yeah, it's a starting point, but yeah.
Yeah, I think a major problem we're having with customers is they're trying to design their complete circuit using SPICE, and they're amazed and confused when suddenly their circuit is not working the way they want it to.
Yeah.
And it's because they're trying to push the limits of SPICE. SPICE is fine for optimization, but the circuit has to work to begin with.
Yeah.
You know. So you shouldn't rely on SPICE to design your circuit. It is not a replacement for a breadboard, but you should test your circuit out in hardware before you go to, or besides relying on software. It's good for optimizing, but it should not be relied on.
Well, wait a minute.
I wouldn't say optimizing. It's good as a first cut. You're going to optimize with your breadboard.
You can peek and tweak with it, but you have to have an understanding of the circuit to begin with.
Man.
I think a lot of people are relying on SPICE and canned circuits that, I will put in this number and I will get this number out without understanding what's going on inside the black box.
Paul, you have an excellent point there. and Bob, that brings us back to your point. If you don't understand where you're starting from.
Exactly.
How in the devil are you going to get to where you want to go? So you have to know where you're starting from. You have to understand the components you're working with, you have to understand the results you want, and you have to have a pretty good idea of how to get there. And SPICE is not going to give you that answer.
SPICE is not only a crutch, sometimes it's a rubber crutch. You depend on it, and you fall down because SPICE doesn't understand what you're doing, and worst of all, you don't understand what you're doing. Oh, man. So we keep running into people who rely on things like SPICE, and every time they rely on SPICE, it's like getting home 10 times in a row and crashing into a bridge on the 11th time. Well, guess what? My boss wants me to have things that work better than 10 times out of 11. It has to work. So if it crashes and the customer crashes, 10 customers out of 11 happy is not enough. SPICE, I don't trust SPICE. SPICE is so often a rubber crutch, we just don't trust it. And when customers do, I'm sorry, but they have a problem. Okay, final topic. To end up, a reminder, we do invite your analog questions. You can send them to rap@galaxy.nsc.com. Hey, if I leave this about 4 seconds more, people can always see what this is, right? This will be remembered enough on video, right? We'll see you in a month, and thank you for tuning in to the Bob Pease channel of National Semiconductor Corp. In behalf of Mr. Gray and Mr. Goey, thank you very much.
Thank you, Bob.
Bob?
Thank you.